So far in this course, we've talked quite a lot about sum sets, and recently I've introduced the topic of discrete Fourier analysis. And in this video, the two subjects are going to come together because we're going to use Fourier analysis to analyze, well, something to do with sum sets. And the thing to do with sum sets is to do with the structure of sets with small sum set. So more precisely, the question that's going to interest us is the following. If a set A, so A is an additive set, that is a subset of an Abelian group, a finite subset of an Abelian group. If we know that it has a small sum set, and that's going to mean that the size of the sum set is at most some constant times the size of the set. So let's just say if that's the case, then what can we say about A? And the answer is we can say a surprising amount, because it's a rather, in a sense, a rather weak assumption. It's just about cardinalities of the sum set, and yet the information that we're going to be able to get out of that is a strongly structural piece of information. Before I dive into actually starting to give a proof of a statement which I haven't yet told you, I want to think of some examples of sets that have small sum set. So in a question sheet I asked you various questions, not perhaps precisely this one, but questions similar to if you know that, say, the size of the sum set actually equals the size of the set. So it's that's just saying that the set is closed under addition. That just says it's a subgroup. And if the difference set has the size of the set, then it'll be a coset of a subgroup and things like that. Oh wait, sorry, that's not true. That doesn't say that it's closed under addition. But nevertheless, no, under this circumstance one can prove that it's a coset of a subgroup, I beg your pardon. Now another observation is that if the size of A plus A is CA and B is a subset of A, and B has size at least, I don't know, theta times the size of A, then obviously the size of B plus B is less than or equal to C times the size of A, which is less than or equal to C theta to the minus 1 times the size of B. So if we regard being bounded above by some absolute constant C times the size of the original set as being our measure of having a small sum set, then if I take a subset of A that's of proportional size compared with A, then B will also have a small subset. So any kind of structural information that we can hope to get about A is always going to have to be of the form A is contained in, or is a large subset of something or other about which we can say something. So just because whatever we can say, if we pass to whatever we can sort of conclusion we can draw about A, unless you're looking at very, very fine quantitative details, if we pass to a large subset of A, we'll still have a set with with a small sum set, and therefore the structural property that we get will have to be closed under, so to speak, closed under taking large subsets. So a very, very optimistic conjecture at this stage would be to say that if A plus A has size at most C times the size of A, then A is in fact a large subset of a coset of a subgroup. But to see immediately that that's false, let's have a look at the set A subset of Z, A equals 1 up to n. Then we have that A plus A is less than 2 times the size of A, as long as n is bigger than 1. But it's certainly not the case that A is contained in a coset of a subgroup that's not much larger than A, because Z only has trivial subgroups, and so A is not even contained inside a finite subgroup of Z. So that's too much to ask for, but what we'll find actually is that, I mean, the problem here was that Z didn't really have enough subgroups, hardly had any. But if we look at something like Fp to the n for some very large n, then counterexamples like this are not so easy. By p I think of some fixed small prime like 5 or something. It's not so easy to come up with counterexamples of this kind, and we will actually find that if A plus A has size at most c times the size of A, then in that particular case A will be contained inside a subgroup of Fp to the n of size not much larger than A. And that's trivially a sufficient condition by the observation we've just made up here. So in the case of Fp to the n, we have a situation which I shall prove not in this slide, not in this video, but in the next one, or in this one and the next one. We have the situation where a trivial sufficient condition, or it turns out to be necessary, or there is a sort of easy set of examples to write down, and it turns out that's everything. In the case of subsets of Z, actually there's a slightly similar situation arises, and I'm not going to prove this in full, but I'm going to prove quite a big part of it. And so let's just think. We could make a very optimistic conjecture, having written down this example, that the only way of having a small sum set is to be a large subset of an arithmetic progression. Again, it's always got to be a large subset of something. So maybe the sort of thing that you're inside that forces you to have a small sum set always has to be an arithmetic progression. We sort of think of an interval like that. And it would be, if we had time, I would set as an example, a question on example sheet, is it true that every set with small sum set is a subset of it's a large subset of an arithmetic progression if it's in Z? But I'm not going to ask you that exercise, but if you've taken on board something that we have talked about, which is that finite subsets of Z to the D are isomorphic to subsets of Z of whatever order you feel like, then you realize straight away that you could, in Z squared, it's quite clear that another way of having a set with a small sum set is to take everything in integers from 1 to n cross integers from 1 to n. So that's going to expand by 2 in that direction and 2 in that direction. So basically it'll be a bit less than 4 because it's 2n minus 1 times 2n minus 1, but effectively, essentially when n is large, it goes from n squared to 4n squared. And of course we can take, in Z to the D, we can take a grid. Doesn't have to be the same length in both directions. We can take a d-dimensional grid and get an example that way. And so we can take these examples and project them down in a suitable way into Z, and we get things that are known as multidimensional arithmetic progressions. So a simple example of a multidimensional arithmetic progression would look like this. This is a two-dimensional one. So we have a few points there, and then we have a sort of gap, and you can think of it as a progression of progressions, or you can think of it as a projection of a grid. I happen to make this a 4x4 grid, but as I said before, the number of, perhaps I'll make it a 5x4 grid just to emphasize that point. It doesn't have to be the same number of things here, of course, as it is in each piece. So we have all those examples as well, and then that turns out to be enough by a famous theorem of Freiman, that if A plus A has size at most c times the size of A, then there exists, and I'm not going to write this out very formally, but there exists P, let's call it a d-dimensional arithmetic progression, where that's a two-dimensional one, and the d-dimensional one is just a projection of a grid inside z to the d, such that the size of P is at most k times the size of A, and A is a subset of P. And I haven't said anything about what D and K are, but I will say D and K depend only on C. So I've got to have something like that to make it an interesting statement, otherwise I could just stick A inside an arithmetic progression that goes from the minimum of A up to the maximum of A. But the point is that P is not allowed to be much larger than the size of A. And a similar remark actually applies to, actually I'm not quite sure, but it's important that D should also be bounded just in terms of this constant C. So what I'm going to prove in this course would be a somewhat weaker statement than this, but one that is sufficient for most applications. And then I'll say a little bit about how you get from what I do to this full statement of Freiman's theorem. But I will give a complete proof of the fp to the n version of Freiman's theorem. Now, I said there would be some Fourier analysis, and that's the main thing I want to talk about. But before I do that, I can need a definition. Sorry, I've got something in my throat. Let G be a finite abelian group. And let, well, actually I don't want to let and yet, because I've got three things in this list. Let chi1 up to chi k be characters on G, and let delta be greater than 0. Then the Bohr set be chi1 up to chi k delta is the set of all x in G such that chi I x belongs to the set E of minus delta up to delta for all I equals 1 up to k. Now just a quick reminder, E of alpha means e to the 2 pi I of alpha. Chi I of x is going to be an element of the unit circle. And so the image under the function e of the interval from minus delta up to delta is going to be a sort of closed arc of the circle that will go from minus 2 pi delta. So what I really mean is that angle there is 2 pi delta. So e to the minus 2 pi I delta, and then that angle there is also 2 pi delta. So we think, well, sometimes we care about delta being small, sometimes we allow it to be, it doesn't have to be too small. Right, so let's just think about what this Bohr set is in the case where the group G is fp to the n. So if G equals fp to the n and chi I is chi of ui, so I'll just remind you that chi ui of x was e of ui dot x over p. So if delta is less than 1 over p, then chi ui of x belongs to E minus delta delta if and only if ui dot x over p belongs to minus delta delta, sort of mod 1, let's say. But ui dot x is an integer, or a residue class of an integer, but let's just call it an integer. But and the main point is that ui dot x over p is a multiple of 1 over p, and so if delta is smaller than 1 over p, so this implies, well, this is true if and only if ui dot x equals 0, where the equals is mod p, but I'll just put that symbol to emphasize it's a mod p equality. So in that case, so b of chi 1 up to chi k delta, again still assuming that delta is less than 1 to the p, 1 over p is the set of x such that ui dot x equals 0, I equals 1 to k, and assuming we haven't taken the trivial character amongst any of the ui's. Well, actually, I don't even really need to say that. So it is a subspace of codimension at most k. And of course, if it's got codimension less than k, that just means I chose some linearly dependent ui's, and I can throw one of them out. So it's not a sensible way of defining this Bohr set to take characters that are linearly dependent, because you can always just chuck out a few until they are linearly independent. And if they are linearly independent, then the density of this Bohr set will, of course, then be p to the minus k. So in that case, Bohr sets are subspaces, and what we'll find later on is that Bohr sets are a little bit like subspaces, also in the case of cyclic groups, and they're also a bit like multidimensional arithmetic progressions, although they're not the same as either of those things. Okay, so with that remark out of the way, I would like to prove a very important lemma, and this is going to be the last thing I do in this video. So it's Bogolyubov's lemma. So let G be a finite abelian group. This time I didn't, that wasn't a mistake, I actually wanted it to be a finite abelian group, not just any old abelian group. Because I want a subset that has a density. Then (2a minus 2a) contains a Bohr set of dimension. Now, I forgot to say what the dimension of a Bohr set was, but I'll say it in a minute. It's the number of characters you need in order to define a Bohr set, so just so you understand while I'm writing it. A Bohr set of dimension at most alpha to the minus 2. So the dimension of b chi1 up to chi k delta is at most k. That's the definition of dimension. One other thing I also want to say, and width less than a quarter. A width a quarter, sorry. And the width is this delta. So that's just... So I beg your pardon, I should have defined those things before stating the lemma. But this will do. And the proof turns out to be a fairly simple application of just the basic tools of Fourier analysis, but everything comes in. So we want a condition for an element x to belong to 2a minus 2a. And I said that we like concepts that translate nicely into the Fourier side, and unfortunately if you take the characteristic function of a, which we will do, and then you look at the characteristic function of 2a minus 2a, and we look at the Fourier transforms of those two characteristic functions, there isn't a nice relationship between them. So we can't do Fourier analysis in a terribly direct way. But what we can do is, and something that does translate very nicely into Fourier analysis, is to define so this isn't really part of the proof, it's just the statement I'm pondering. I'd like to find some way of taking this statement and translating it into the Fourier side. So we'll let f of x be the average over a plus b minus c minus d equals x. I'm going to write it in a different way. Sorry. I'm going to say a star minus a star minus a of x. So so that is average of what should I call them? P plus Q minus R minus S equals X of 1A of P, 1A of Q, 1A of R, 1A of S. So this is counting the number of ways of writing x as p plus q minus r minus s, where p, q, r, and s all belong to a. When I say counting, there is a normalizing factor because we're taking this average. If I took the sum, it would be counting exactly this thing, but in fact it's taking the size of g to the minus 3 times the sum. But that doesn't matter, because all we care about is that then x belongs to 2a minus 2a if and only if f of x is non-zero. And the point is that we've expressed f as a convolution evaluated at a certain point x, And convolutions are very, very nice things. Oh, so by the way, I did something that I warned you that I would do, which is this a is in fact the characteristic function of a. And here I wrote it as a characteristic function, but here I just wrote it as a. And that's something I like doing. So you can't, strictly speaking, convolve a set with a set, but you can convolve its characteristic function. And if you just kind of think of the set and the characteristic function as being essentially the same thing, then writing this is fairly harmless. So actually I'm going to drop the 1a because it's slightly tedious to write, and I'll stick with the a from now on. So now we just hit it with Fourier analysis. We know that we can because we've got a convolution in there somewhere. So what is f of x? It's, well, let's just write this again. Evaluated at x. And that equals, by the inversion formula, the sum over all chi of a star minus a star minus a massive great hat of chi times chi of x. And what is the Fourier transform of this convolution? It's just the product of the Fourier transforms. So it's the sum of chi of a hat chi squared times minus a hat chi squared evaluated at x. And if you think about it for a second, well, let me do a little calculation because this is a basic property that I forgot to mention amongst some of the other basic properties, but we can quickly do it now. So minus a hat of chi equals the average of a of minus x chi of x bar. But then I can substitute minus x for x, and so that minus x becomes an x, and that x becomes a minus x. So that, and chi of minus x bar is the same as chi of x. So we can just get rid of the bar there and get rid of that. But this is exactly the same as the definition of a hat of chi, except I've forgotten to put a complex conjugate over this, and this one's a real number. So this is in fact just a complex conjugate of a hat of chi. So this relies on the fact that this is a real valued function. So if I define, more generally, if I define f minus of x to be f of minus x, and if f is real valued, then f minus hat is a complex conjugate of f hat. So having done all that, let's just get rid of it again and say that this is equal to the sum of chi times the fourth power modulus of the Fourier coefficient at chi evaluated at x. And now we want to show that it contains a Bohr set. So in other words, we want to show that f of x is going to be non-zero for all x in some Bohr set. And I haven't defined the Bohr set yet, and here we go. So let B, first of all actually, let K be the set of all chi, characters chi, in the dual group, such that a hat of chi has size at least alpha to the 3 over 2. And of course it's not obvious that alpha to the 3 over 2 is the thing you should write down here. What I could do is write eta, where we'll choose eta later, and if we do that we find that we'd like to take eta to be alpha to the 3 over 2. I've done this a few times, so I know that it's alpha to the 3 over 2, but of course there wasn't some magic foresight in choosing that. It was just something that comes out at the end of the proof. And actually the same thing applies. B equal B K a quarter. Well, that's just shorthand for b chi1 up to chi k, where chi1 up to chi k are the elements of k. Perhaps I could say k not including the trivial character, because that doesn't contribute anything. So having done that, I'm going to split up f of x into 3 parts according to whether the character is 0, or the trivial character, or whether it belongs to b, or whether it doesn't belong to b and is non-trivial. So then f of x equals, so we've got this formula here, so let me move that up to the top. We know that that equals f of x. So what happens when chi is the trivial character? Remember, A had density alpha, which means that A hat evaluated at the trivial character equals alpha. So we get something's wrong there, and it was wrong there as well. I wanted a chi of x. Yes, because this chi over x just carries on down here. So back to here, so we get, and what is, when chi is the trivial character, chi of x is just 1. So we get alpha to the 4th times 1, so let's just put that in, alpha to the 4th, plus the sum over all chi in B of alpha hat of chi of x, plus the sum over all chi not in B and chi not equal to chi 0 of alpha chi to the 4th chi of x. Now let's just think about what we can say about this. So if x belongs to B, then chi of x belongs to E of minus a quarter for all chi in B. That's the definition of this particular Bohr set. But E of minus a quarter is everything from minus pi over 4 up to pi over 4. Sorry, 2 pi over 4 up to minus 2 pi over 4 up to 2 pi over 4. So in other words, minus pi over 2 up to pi over 2. So that's what we've got here. So in particular, the real part of all of these things, beg your pardon, the real part of all of these things in this sum will be positive, and this is just a positive number. So we get that the real part of the sum over all chi in B of A hat of chi to the 4th chi of x is greater than or equal to 0. And now let's look at this bit here, but also the modulus of the sum chi not in B, chi not equal to chi 0 of A hat of chi to the 4th chi x is less than or equal to, just by the triangle inequality, the sum over all chi not in B and not equal to the trivial character of A hat chi to the 4th. And now we'll use the L1 L infinity inequality to bound this above. So what is the biggest that any one of these things could be? Or let's forget the 4th power. What's the biggest that any one of these A hat of chi's could be? It's strictly less than alpha to the 3 over 2, because that was, again, how we defined the Bohr set. The Bohr set was a set of things that were at least as big as alpha to the 3 over 2. So I'm going to say that the square of this thing is at most, sorry, is less than alpha cubed, and then the rest is at most the sum of all alpha chi squared. Now notice I'm summing here over all chi instead of chi that don't belong to B and are non-trivial. That just makes things bigger, so I'm allowed to do that if I want, because it's on this side of the inequality. And then that allows me to apply Parseval. I know that the sum over all chi of A hat of chi squared is just equal to the density of A. So that equals alpha to the 4th. So now let's have a look at what we've just done. We've shown that f of x is equal to alpha to the 4th plus something with non-negative real part plus something of size strictly less than alpha to the 4th. So that's therefore the real part of f of x is greater than 0, so f of x does not equal 0. Therefore, this Bohr set B is a subset of 2a minus 2a. Because what I've just shown is that for every x in 2a minus 2a, which is the same as every x, for every x in B, we get that f of x is non-zero, but f of x being non-zero is equivalent to x belonging to 2a minus 2a. Now I haven't finished the proof because there's one last detail, which is a very important detail, which is that I promised at the beginning that the dimension would be at most alpha to the minus 2. But that again is easy, but by Parseval, alpha is the sum over all chi of A hat of chi squared, as we've just seen, which is greater than or equal to the sum over all chi in K of alpha hat of chi squared, which is greater than or equal to alpha cubed times the size of k, because each of these things for chi and k is at least alpha to the 3 over 2 squared, i.e. alpha cubed, and there are k of them. And so therefore the size of k is less than or equal to alpha to the minus 2, as promised. And that ends the proof of the Bogolyubov lemma. Now, what we're going to... So actually what we've already seen, because I showed you that in the case of fp to the n, so I'll finish with this remark. So if g is fp to the n for some n, then this shows that 2a minus 2a contains, where A is a subset of G of density alpha, contains a subspace of codimension at most alpha to the minus 2. So that's the same as saying dimension at least n minus 1 over alpha squared. So that is already a fairly non-trivial statement. And what we'll see in the next video is that you can combine that with a whole lot of other things that we've already proved in the course to obtain the statement I said before, which was that A, if it has a small sumset, must be contained inside a set of inside a subspace that's not too much bigger. But actually, I think if I've given you the clue that using the result that we've just had, now there's one detail that might be a little bit hard to come up with, but I would recommend before watching the next video just thinking a bit about how you might get from something like this to the statement that if A has a small sumset, that it's contained inside a not very large subspace. Because all the tools, except one that I forgot to give earlier, is in place. So I'll give that one extra tool at the beginning of the next video, and then we'll see a proof of Freiman's theorem for fp to the n, and something a bit resembling Freiman's theorem for subsets of Z. But that's it for this one.